Welcome back, everybody. This is part two of a video I posted earlier this week. And the second part of this, we're going to have four problems that are all going to go into kinetic energy and potential energy for a motorcycle crash. So, problem five, we have a crash dummy ejected from a motorcycle. The dummy leaves the bike at an initial height of 1.2 meters, initial speed 22 meters per second, angle of 30 degrees above the horizontal. And we're going to analyze this. So first question asks us to calculate the dummy's initial gravitational potential energy. Formula for this is mgh. So we have 75 times 9.8 for gravity times the height. The initial height is 1.2. And then this equals 882 joules. For initial kinetic energy, we use the formula 1/2 mv squared. So we have 1/2, the mass is 75, the velocity again is 22, zoom in a little, squared. There you go, make it a little better there. Okay, if you plug this into the calculator, you get 19,030, sorry, that's the wrong answer, 18,150 joules. For total mechanical energy of the dummy, it's just going to be the sum of all of the mechanical energies. So gravitational potential energy plus our kinetic energy. So 18,150 plus 882. And then this one equals 19,032 joules. Now we're going to draw an energy diagram. So our y-axis here is going to be our height in meters, and the x-axis is going to be our potential energy as a function of our height. Now this is in joules. So first thing when we're drawing a energy diagram is we want to outline our total energy here. So this is our 19,032 joules. And then this is going to be from 0 to 10 meters. And it's just going to be a straight line like this. And the bottom of it, like the bottom half here, will have our potential energy. So here is our initial potential energy. And then this top part represents, like the distance to the line is the initial kinetic energy. And so this is our 882. And then over here, at a height of 10 meters, this is going to be our potential energy at the apex, if our apex is 10 meters. And then the top part will represent our kinetic energy at the apex. Like so. And then if you're to plug in the 10 meters for our potential energy, you would get a value of 5419.5. Okay. Using the diagram, identify the dummy's turning point and determine the maximum height. So we know that at the apex, so the apex of any arc, our velocity is going to be purely in the x direction. So we can say that our kinetic energy at the top is equal to 1/2 75 times the velocity in the x direction. Well, we know the velocity in the initial velocity is 22 meters per second at an angle of 30 degrees above the horizontal. So if we draw that, here's 22, here's 30, here's Vy, here's Vx. Both of these are initial. But our velocity in the x direction doesn't change. We're neglecting air resistance here. So we can say that Vx, just from trigonometry, is equal to 22 cosine of 30. We can plug that into kinetic energy at the top. And then kinetic energy is squared. So if you plug in all your values, you get 13,612.5 joules. And then the potential energy at the top equals the total mechanical energy. So that's that dashed line minus the kinetic energy at the top. And so this is just our 19,032 minus 13,612.5. So potential energy at the top is that value 5,419.5 joules. And then I'm sorry I misread the answers. This is not the potential energy at 10 meters, it's the potential energy at the top of the apex. But we put it into the graph anyways. So determining the maximum height from this is pretty simple. We have that potential energy is equal to mgh. Now we know potential energy here. We still know mass and gravity, so we just solve this for h. We can divide out mg to the other side. We find the potential energy divided by mass times gravity is equal to our height. So if you plug in 5,419.5 for joules, or for potential energy, our mass is still 75 kilograms, and g, of course, is still 9.8. We get 5419.5 divided by 75 times 9.8 equals about 7.37 meters. Okay. Question 6 says calculate the dummy's final kinetic energy just before impact. This is a little bit of a trick question. We don't actually have to calculate anything. Just before impact, the dummy is going to have a height of 0. And so there's no potential energy. All of our energy, our mechanical energy is potential energy, or sorry, kinetic energy. It's a lot of different energies we're working with. So our kinetic energy right before the impact is equal to just 19,032 joules. Put a little star for impact. And then a final speed at the moment of impact, we can use the same thing from earlier. We have 1/2 mv squared is equal to our kinetic energy, which is our 19,000. We can rearrange for velocity. So we multiply both sides by 2, we divide both sides by the mass, and then we take the square root of both sides to get rid of this 2. And we get the velocity is equal to about 22.5 meters per second. All right, now we're going to analyze the slide. So after the ground contact, the dummy slides a distance of 12 meters before coming to rest. It is a perfectly inelastic impact, so there's no rebound or loss of contact, followed immediately by kinetic friction along the slide. And then we have the coefficient is 0.8. First question, we want to calculate the magnitude of kinetic frictional force acting on the dummy. Well, we know that this is just going to be, our force of kinetic friction is just mu sub k times n. Again, the dummy weighs 75 kilograms, so this is just zero 0.8 times 9.8 for gravity times 75. And then this equals 588 newtons. Work done by friction over the 12-meter distance. The equation for this, so we'll say work of friction is going to be negative frictional force times the distance traveled. So this is equal to negative 588 times the distance is 12 meters, and this equals negative 70,056 joules. And then the sign we've already stated as negative. What that means is that the friction is opposing motion. In other words, it's causing the dummy to slow down. Question 3 wants us to write an expression for the initial kinetic energy of the dummy at the start of the slide and calculate its value. We've kind of already written an expression for kinetic energy up here due to work. We know that work done on a system is equal to the change in kinetic energy. And so if we have the work of friction and we know no other forces are doing work, in other words, there's not any air resistance or, somebody's not trying to speed him up or slow him down, we can say that this value is equal to the change in kinetic energy minus without the negative sign. So it's just 70,000 or 7,056 joules. Final kinetic energy at the end of the slide, well, he's not moving at the end of the slide, so final kinetic energy is just 0. And then apply work energy theorem to verify your result. Is answer consistent with the change in kinetic energy? Well, we have change in kinetic energy is equal to K initial minus, or sorry, this is K final minus K initial. K final we found to be 0. K initial we found to be 7,056. And so, yes, we get negative 7,056 joules, as one might expect. Mechanical energy lost through friction is converted into thermal energy at the road dummy interface. So the corresponding increase in thermal energy is our 7,056 joules. So all of that is converted into thermal energy. So we have to discuss whether the system can be considered isolated over this process. What energy forms remain within the system and which are dissipated to the environment? And the answer is that, everything is converted into thermal energy. Some of it is thermal energy that is present on the road, some of it is present in the body, and the rest is lost to the air. Since we're only considering the dummy in the road and not the air, we can't consider it to be a perfectly isolated system because some of that thermal energy is dissipated to the air and the environment around it. All right, now somebody has the brilliant idea to give the dummy a helmet. Very happy for our dummy. His head weighs 4.5 kilograms. It hits the ground at 31 meters per second. The helmet's foam can squish or crush 0.035 meters. It's a spring. It can absorb up to 1750 joules before bottoming out. And then, okay, that's all the information you need. So compute the head's initial kinetic energy. We just have 1/2 the mass of the head, which is 4.5 kilograms, times the initial velocity of the head, which is 31 squared. And this equals 2162.25 joules. And then we have 3 cases where eta, which is the fraction of the head's kinetic energy absorbed by the foam, equals 0.6, 0.75, and 0.9. and we're going to consider each of them. So for here we have eta equals 0.6, eta equals 0.75, and eta equals 0.9. So first we want to compute the energy absorbed. We'll call that E absorbed by the liner and state whether it bottoms out. So energy absorbed by the liner is just going to be, this eta is a fraction of how much kinetic energy is absorbed. So if we call this number up here E total, our total kinetic energy, each one is just going to be the fraction multiplied by the total kinetic energy. So here we have E absolute equals 0.6 times E total, which again, E total is 2,162.25. And then this equals 1,297 joules. So it does not bottom out because it has not absorbed 1,750 is the maximum that it can absorb before it bottoms out. So I'll say not up here. What about 0.75? We have E absorbed equals 0.75 times E total. Put these in parentheses so it makes more sense. Again, E total up here. This equals 1622 joules. So again, it does not bottom out. And then finally, we have 0.9 E total, and then this one equals 1996 joules. So this one does bottom out. And then for each eta, compute the energy transmitted to the head and neck. So that's part B here. Cannot draw a straight line very good. All right. So the energy absorbed by the head and neck, we have this absorbed amount of energy by each of the helmets. And so actually, we have one thing to calculate over here. This one, it bottoms out. And so the absorbed energy actually is equal to that maximum of 1,750 joules. Okay. Anyways, the energy transmitted to the head and neck is going to be the total energy. So E total minus the energy absorbed. So in this case over here, E total minus E absorbed is equal to, let me see, 865 joules. Over here, E total minus E absorbed equals 541 joules. And then finally over here, we have E total minus E absorbed equals 412 joules. Okay, now cases without bottoming out, so just cases 1 and 2, calculate the average and maximum force borne by the helmets. So in this case, it would be for average force, we'll do that first. Force average is going to equal the energy absorbed divided by the distance. And again, this just comes from the equation that changing or work equals force times distance. And since work equals change in kinetic energy and the energy is being absorbed, it's all the same thing. And our distance, our crush travel listed here is 0.035 meters. So I'll write that here. D equals 0.35. Or sorry, that's 0.035. There we go. So in this case, our average force, our energy absorbed 865 divided by 0.035, we get 3.71 times 10 to the fourth newtons. Over here, our average force, again, will be energy absorbed. Oh, I'm sorry. It's for this one, I said it was 865, but the absorbed energy is our 1297. So it's 1297 divided by 0.035. Over here, we have 1622 divided by our distance, 0.035. And then this, apologies for the audio cut there. I had an alarm on my phone go off. But our average force we calculated here is the energy absorbed divided by distance, which is 4.63 times 10 to the fourth. And then the maximum force borne by both of the helmets, force max. Since up here we have our average force, the maximum force is just going to be 2 times the energy absorbed divided by the distance. And so in the first case, this equals 9.27 times 10 to the fourth. And in the second case, this equals 2.36 times 10 to the fourth. Second question here says for the cases which bottomed out, so this final third case, again, calculate average and maximum force, but this time borne by the head. So this value is the energy borne by the head. So we'll call this E head. And then it is the same equations. So average force is going to equal E head divided by distance. And then maximum force will be twice E head divided by distance. And the two values for this are 1.18 times 10 to the fourth newtons and 2.36 times 10 to the fourth newtons. All right, final question. So now our crash dummy is wearing an inflatable airbag on their torso, and all of our important information is already given here. So first question asks us to calculate the mechanical work done by the expanding gas during inflation. So work done by a gas is equal to the pressure times the change in volume. So we have 5,500 times 4.5, and this will equal 2.48 times 10 to the fourth joules. Average power output during the 0.1 second inflation. So average power will equal the work done by the gas divided by the time that that takes. So this is our 2.48 times 10 to the fourth divided by our time, which is 0.1. And this will equal 2.48 times 10 to the fifth. And then this is power, so this is watts. Question 3, given 25% efficiency from chemical to mechanical work, determine total chemical energy that must be stored to produce this work. So our eta is equal to 0.25. And then this is equivalent to the work of the gas divided by the chemical energy. So rearranging this, we can say that our chemical energy, erase to give myself more room, but our chemical energy is equal to the work done by the gas divided by our eta, which is 0.25. And then this equals 9.9 times 10 to the fourth joules. 4 asks us to calculate maximum elastic potential energy the vest can store at full compression. Equation for maximum elastic potential energy is given by 1/2 the spring constant, K, times the compression distance, which we'll say, actually, we'll call that delta X squared. So in this case, our K, our spring constant, is 45,000 newtons, and our compression distance, or delta X, is 0.02. If you plug these values into our equation down here, we get that the maximum elastic potential energy is about 9 joules. Question 5, assume 40% of body mass corresponds to the torso, and using the dummy's mass from part 1, estimate torso mass and kinetic energy before torso vest engagement. So from part 1, we had that the dummy weighed 75 kilograms. 40% of this is about 30 kilograms. And the speed that he had earlier was 22.5 meters per second. So we use 1/2 times 30 times 22.5 squared. And then this equals 7.61 times 10 squared joules, or just 761 joules. So the elastic potential is only 9 joules, and the kinetic energy of the torso is 761. So it's really not absorbing like any energy. Question 6 asks us to redesign the vest to increase energy absorption without exceeding safe chest compression limits. So the best way to do this, if you look at our spring constant here, or our spring equation here, the culprit for why we have such a small value, we have 45,000 for our spring constant for the inflated vest. Like that's plenty big enough. But then we multiplied it by 0.02, and then we squared that. And if you square 0.02, you get 0.0004, which is a very small coefficient. So the best way to redesign this motorcycle airbag vest is to kind of increase the size of it, or increase the compression distance so that the force is decreased proportionally. So if you can make this number bigger, then it will really increase the maximum elastic potential energy. But that's the end of this video. Again, this was part 2 of the previously posted video. Thanks again to Krish, who makes these packets, and I wish you all best of luck in your studies.